So, hi everybody, I am Kashif Murali. I am one of the co-deans with Vinicius. He taught the machine learning class yesterday. And today's class, and in general the course for the next 4 weeks, is going to focus around natural language processing. So, anyway, natural language processing is how we deal with text. We have text all across Google, Wikipedia, Google Books, etc. And the whole point of natural language processing is how can we harness this text and get more data and insights from it. We taught, I taught this course last year as well at March, right here. So although for people who have come here before, the material might seem a little bit same, but in the beginning, but later on I'm going to restructure it because there have been more research developments from Google, Microsoft, Baidu. So essentially later on in the third or fourth week we are going to take it on from there.
Is there a link someplace else?
Yeah, I was just about to put that.
Because I can't get into it.
And the link for this is, if everybody can go to our meetup page, which is meetup, and then click on today's event, you will get here. There we go. Click on today's event, scroll all the way down, and in the comments I've added the Colab link. So yeah, I'll just wait for everybody to get there. And a brief, intro about today's session. It's going to be about understanding existing language models, which can be applied easily to the industry. And in the future, we're going to be delving down into the technical details. So today we're going to see what is it and how and what it does. And in the future, we're going to be looking at how it does what it does and what different competitors use to build better and better language models. So once you open this, you're going to get into something very, very similar to this notebook. But the problem should be that you would not be able to edit it. So if everybody who's at the stage, then you can click File, and then Save a Copy in Drive. That will allow you to edit it and make your own personal copy, which you can do all sorts of sandboxing and testing. And for the sake of runtime and or storage space, because this is on the cloud, there'll be some shortcuts that I'm taking. I'll explicitly mention those shortcuts, but the point should still be the same, how the concepts work. Any questions so far on how to get here? And I can come around and help if need be.
It's just in the comments below.
Yes, it is. You go to the event, you scroll all the way down, and it's the comments. And also, if anybody has not had the chance to fill in this Google form, it'd be much appreciated if you could do so. That'll help plan our courses better. And tomorrow is going to be the Python for Data Science course, I believe, with people coming from Bloomberg and teaching here. And for those who are not, completely thorough with the language of Python, they can come and learn, how we can use that in these kind of applications. Because this assumes that you have a fundamental knowledge of Python and a fundamental knowledge of machine learning. Okay, so let's get started. As I said, today we're going to look at existing language models and how, what it is, what they are, and how we can use them. So there are many out there. Some you may have heard of, something called NLTK, which is Natural Language Toolkit. Another is SPACY, Stanford Core NLP. They're all different beasts which kind of do very similar things.
Can you walk us through the content of the class?
Sure, yeah. So as I mentioned earlier, today is going to be understanding what language models are, right? And what they do. Like, how can you physically use them? There's this term that gets thrown about. How do we first build the foundations of NLP? How can we write our own first application that there's some pre-processing steps that need to come to it, like turning a word into numbers. And how exactly are we going to do that, and how the industry does it? So it's just an analysis, from an outside's perspective, how industry would do it, and what it does. Is that okay? Awesome. So SPACY, as I said, SPACY, NLTK, Stanford Core NLP, they all do very, very similar things. But in this case, I'm going to use SPACY because it's by the order of 400 times faster in splitting sentences into words, and a lot of fundamental NLP stuff. It's pretty fast. So I chose SPACY. Now, you can do many things with it, but NLP kind of boils down to a couple of things. One is tokenization. So an important piece is you have a sentence, let's say, I am going to the park. and you have to split it into I, comma, am, comma, going, comma, to, comma, the, comma, part. And that seems pretty easy, right? You just find the space and split it. But obviously there are many variations to text. There are commas, there are periods, exclamation points, some other details that you need to deal with. And therefore, the first primary step in the pipeline is to split the words into split the sentence into individual words. Then once you do that, you can do many different things with it. And just for like a brief teaser, one thing that you can do is identify how different words are dependent on other words. For example, the library is it's the word awesome. The adjective is referring to library, and you can see in these dependency parser maps. Another thing you can do is find out entities within the text. NJ Princeton Public Library. That's another thing that you can do. So today I'll also be exploring the different things that you can do with this language model. Awesome. So first step, as with any Python program, is to generate, is to put in our imports. So I'll first create the language model, and something fun is we're going to apply this to the real world. We're going to create a Twitter sentiment analysis, detector. You give it any keyword, you put it in, it'll fetch the tweets, fetch the text of the tweets, and then split it into positive sentiment and negative sentiment. And we're going to visualize that in the form of a word cloud. This is kind of the project that we're going to do today. Awesome. So we have our imports as a spacey is for our language model itself, which I'll explain shortly. Pandas is how we deal with data frames, data structures. And this word cloud and text blob, we can use that for, it's just a third-party API in order to find the sentiment of the text, and also, generate the word cloud that I was talking about earlier. So as I said, now let's talk about what these language models do. So you can't just put a word into a computer and expect it to understand what it does. The first step is to convert it into numbers, right? Now there are many ways of doing this. Now if you just pick our brains and let's just choose some really basic way. If there's a sentence, I am going, I'm happy, let's make it simple. I am happy. One simple way of doing it is create a list. So everybody here knows what a list is, right, from Python? If not, tomorrow's class will enlighten that and will make it a bit easier to understand. But essentially you can have a small list of 3 elements, and each one represents a word. So I is represented by this, am is represented by this, and happy is represented by this. It's just a vector. Now how would I represent the word am? 0, 1, 0, 1, 0. Because it's like turning a switch on, right? I'm turning the switch of am on. Now this is a really basic way to do it. But now if you imagine with the English vocabulary, this list can get huge. Because for each and every word, you have a new vector of the entire size of the vocabulary that you're creating. So like 30,000 words is, for each representation of the word, you have a 30,000 length vector. And this worked to some extent, and it's still used today. In some cases, the field progressed into something a bit, more intuitive. How do we find the similarities between words? I want to know what a word is in relation with another word. So for example, now think in terms of analogies. So if king is to queen, then man is to woman, right? That's the analogy. Now how do you create these kind of similarities? Like what does the word mean based off the context? They actually made it pretty interesting. They converted the words into coordinate points. So if you can imagine like a 2D coordinate plane, alright, Spark is dead. But as I said earlier, if you can imagine a 2D coordinate plane and you fed in, a lot of sentences, you need a lot of data to train this. So you fed in the entirety of, Shakespeare. In a 2D coordinate plane, you'd get the words bird, dog, and over here you can get car, bike. Point being, similar words are structurally related to each other. So now if I want to find the distance, if I want to find the similarity, it's just a matter of distance. What is the distance between point dog and point bird? That'll give me the similarity of dog and bird. And the farther away it is, the less similar it is. So let's give the point 1, 1 for dog, and for bird the point is 1, 2. Then the distance just becomes 1, and that's pretty similar if you consider bike would be -1, 1, where the distance is a lot bigger. Now this is a way of unsupervised learning because you're not giving labels to start off with. You're not saying bird has to be, like you're not saying bird and dog is like similar. You're not, that's not what you're feeding in. In a context, in a sentence, you're just feeding in, you know, I have a bird, and another similar sentence could also be I have a pet, and there could be like millions of sentences or thousands of sentences or whatever. And based off of that, it'll figure out what the similarities of the words are. There are different ways to do this, and I'll just quickly go over them. One is predicting the center word. So given the context of all the other words, what will the center word be, and how that depends on the relation of each and every other word. And a different one is, given only the center word, you're predicting the other words. Now that's not really a big deal, we'll go over that later. Today is just to understand what it is, and that's just a coordinate grid. So it's like a lookup table. I have a point, I have a word, and I'm finding the coordinate vector of that word. Now it's not really two dimensions, it's in the order of like, depends on how much data you have, 64, 128, 256, they tend to do it in orders of 2. But that's it essentially, that's what it does. It plots points on a coordinate grid. That's great. So now first let's load our language model. Now Spacey makes it really simple, they have pre-trained language models. And it's in 3 different sizes, SM, MD, and LG. And you know what, I'll show that to all of you. Spacey.io. It's great because it does a lot of different things. 1 second, I'll find English. All right. So the first one you can see is n_sm, which should be available here. n_sm, that's a small version. Then the n_md, the medium version. LG is the biggest version. And then this is for what I was talking about, those vectors, you know, those similarity. If you don't want to do any other different pipelines, you don't want to do named entity recognition or whatever other use cases, there are different compartmentalized models. And of course, there are ones for different languages, you know. You have Portuguese, you have Spanish, you have French, whatever. But obviously, some of them aren't as good as English, simply due to the data that is available to train off of. But you know, they try to make it as accessible as possible. So far, are there any questions on what these language models do and why we need them?
Well, yeah. So, is the model has just created all the vectors? Is that all it does, or what else does it do?
The word vector model finds the numerical coordinates of each and every word. So for words that are in the vocabulary, right? If you give a random word, it won't be able to find any coordinate because it didn't exist before. But if I trained on a couple of sentences in Shakespeare, or like thousands of sentences in Shakespeare, for each and every word that is mentioned within that text, each and every unique word, it'll give one point. It'll give a point saying, the represents 1, 2, and like, he represents 1, 3 or something like that. So it'll give a coordinate point for each and every system. Now, if you think about it, there could be flaws with this. Say the whole I am, right? Okay. Say the sentence we can do this, right? Versus Coca-Cola is shipped in a can. This method right here, the word can is the same representation for both, like the first can and the second can. Now that's like a glaring issue, right? Based on different contexts, we want different different coordinates in order to make better predictions. And we'll be discussing that in future classes, but that is what contextualized models, if you may have heard of it, BERT from Google, there's Elmo, and there are just a couple of others that you can use. GPT. GPT-2 is actually great because there's some sort of issue going on that it's dangerous for society. That's why they're not releasing it. That's whatever. But the point being, they're better models which, based on the context, it'll give newer representations. So far so good?
Sorry for the interruption. What are the 5 comments that are saying when you do live is not working?
Okay. 1 second, I'll go check it. But yes, in the meantime, I'll pull this up and I'll share that back to this. You know what? Since the YouTube live link is not working, I'm going to start by showing you a visualization of what I'm talking about. So if everybody could go to this thing called projector.tensorflow.org, you'll see exactly what I'm talking about in terms of the definitions and how the words are in a coordinate plane. So you can explore it, zoom in, and see how similar words are quite literally closer together. Now it's a 200 dimension thing that I was talking about with 10,000 unique words. So it's just dependent on the number of words. But while you're exploring that, just a brief couple of minutes, I'm going to quickly look at this YouTube live problem and see what it looks like.
All right. So, gotcha. So, are these models like word embeddings, or they're more than that? Or they're
No, these models are word embeddings. These models are literally word embeddings. But the ones that I talked about earlier, which BERT, Elmos, GPT, they're not word embeddings. They are like language models, quite literally.
language models. So you have language models like name entity recognition.
Sorry?
You have models, neural language models like named entity recognition that are trained on something and that read input and spit out tag or whatever. Okay.
Yeah,
But what you were talking about was embeddings, and they're already they've been fitted already. So they're coefficients
exactly.
basically. Yeah.
You can fit embeddings yourself, like with new data. I'm not going to show that in this class, but that's a possibility. And is the YouTube link working, or is there some sort of issue with it? Like,
Is what working? The embedding projector thing?
No, the YouTube link itself.
Oh, I don't know. Is it working yet? Take a look. I'll take a look. Yeah. What's the URL for it?
It's on the comment section of the meetup.
Oh, okay. Hang on.
Thank you so much. While that's going on, though, this is being recorded, so there's no big deal. We can just upload it later.
Kasha. Back to spacing. So how is it different from NLTK? Is that, what's the...
NLTK is a bit different than Spacey. One is the way they do it, the speeds at which they do it, and also fundamentally, Spacey has a lot more components than NLTK. So if you go to this usage,
So it's not on here.
these pipelines, these processing pipelines
Yeah, so what
that
is your-
are, this you can look at the documentation itself. But the ability to build these processing pipelines don't really exist in many other of these NLTK or standard kernels. The speed is also slower, and however, it does the tokenizing, it does the stock voice detection, it can do all the pre-processing, pre-train, but these pipelines itself don't exist. So the industrialization aspect is not available in NLTK. That's the main part.
So that's the strength, is that it has a pipeline.
Yeah, that's one of the major
Or
strengths it has.
You're
Yeah.
not connected to a
Processing.
computer.
Exactly, and it has heavy
Did he ask you?
documentation and community support behind it.
Vocabulary and everything.
Absolutely, yeah.
How long would it
However,
take to put it on?
we still do use NLTK because they have the big data sets already like pre-processed. Well, not pre-processed, but packaged. So we do like import NLTK, like brown corpus or something, and that'll like print out the entire like data set itself. So in order to get some data set for like just training a model just for the sake of it, we still use NLTK. So it's not completely useless. It's just that for tokenizing and some other fundamental tasks, we don't use it. We use Spacey just purely because of speed as well.
So is this now standardly used or?
Yeah, I would say so. It's being standardly used because based off the experience, the work experience at least, I haven't seen that many people use NLTK.
Thank you.
Yeah, sure. And if you want to explore this, I think they do have. Yeah, see the feature comparison that I'm talking about. You go to the website and like these and all. Spacey does this is this, but NLTK also does this, and it just does a comparison between the three main ones: NLTK, Spacey, and Stanford Core NLP. And I think there's a speed test somewhere here too. Oh well, whatever. But yeah, that's fine. There we go. Detailed speed comparison is 0.2 milliseconds. NLTK is 4 milliseconds. So it's an order of 443 times for tagging. So it's just a speed differences as well. Okay, doesn't matter. But now we're back to this word embedding. This kind of weird blue-shaped thing is exactly what we're trying to create, and that is those are our coordinates. So each point has 200 length vector. Over here, we had a vector of we had a coordinate system of which is length 2, a vector of length 2. But imagine the same thing across 200 dimensions. It's a bit tough to visualize because it doesn't really make sense how you can have 200 dimensions, but that's essentially what it does. And the more and more dimensions, the more and more complicated it gets. Great. Now to our similarity. So if everybody can see here, we get these points, right? 9.94, 0.83, 0.70. What do they exactly mean? So now there are two different ways of computing similarity. There are actually many different ways of computing similarity when it comes to coordinate system. There's cosine similarity, Jacquard index, Jacquard similarity, Dice index, and some other stuff, which essentially map the union between two sets of points. But to spare the technical details, essentially you can think of it from a scale of 0 to 1, 0 being completely dissimilar, 1 being super similar, I think the same exact thing. So the higher the number, the higher the similarity. That's perfectly demonstrated because I am feeling blue, I am feeling sad, synonyms based off the context. You can see that the similarity over here is pretty high. Now, the one thing to note though is this doesn't dynamically change, even though we know that blue means, like blue could also be the color blue. It's just the fact is that, the word I am feeling that preceded help determine blue being blue. And sorry, I know that confused it a bit, but you can just ignore what I said. I'll explain that another time because it's a bit easier to understand later. It's okay. So now let's find the similarity of two documents. We found the similarity of two words, two individual words. Now let's find the similarity of two sentences, and that's also achievable by spacing. And as you can see here, it's just the coordinate distance of the entire sentence, not just one individual word. The different distance between sentences. Now, interesting thing. This essentially, if anybody's heard of word to vec, is just word to a vector. There's also something called sentence to vec and doc to vec, which essentially has no limit on the size of the input statement that converts into coordinates. Not just words, it'll do entire paragraphs or documents, etc. The bigger the size, generally it gets a bit more inaccurate because fundamentally, if you think about it, the more the words, the more different context that it has. But it's something to explore if it ever comes out of something that you're working on, how you can have an infinite size length and pass it into this vectorizer. Okay, great.
So, can I ask a question about dimension?
Mm-hmm.
So, the number of dimensions is defined by or the program?
It's defined by the user. So you can experiment with different dimensions.
So,
Yeah, but the thing is, Spacey gives it to me pre-trained. This is, they already trained this with. Yeah, exactly. That's why it's the ease of use thing. But otherwise, we have to train it ourselves through dimensions. Yeah. Essentially, okay, now let's talk about one more thing. You can go the long route and use Spacey, or there's just a library called TextBlob. And it's pretty interesting. It has this thing called polarity, which is the sentiment, and subjectivity, which is how subjective or objective, essentially how defined it is by emotions versus data. So essentially, you can also explore other tools. You don't need to always use Spacey, which gives more customizability, for the sake of using. If your only goal is to just find the sentiment, do nothing else, don't waste your time with Spacey, just use something like TextBlob and you'll solve your problem faster. Okay. It's been 30 minutes, so far does anybody have any questions on language models, on word vectors, how we're turning it into coordinates, and what we can do with those coordinates?
This is like word to vec. This is
Yeah, I think Spacey is a different algorithm than word to vec, but it does fundamentally the same thing as word to vec, which is converting the word into a coordinate. Yeah.
So it's pretty much the same.
Pretty much, yeah. But only this aspect is pretty much the same, the creation of the document. There are different things that Spacey does that word to vec cannot do, which is available in the documentation.
This has been trained.
That has been trained already. Yeah. Right.
So is NLP a method inside of this English small?
NLP is a language model itself. So
So you have a class en_core_web_small.load. So you loaded something into that,
Exactly. This
and
is a loading part.
now I see, and so now you're calling this object, the model object, and you've loaded this sentence in it, or actually the sentence or the whole website. Yeah. Okay. Never mind. I think I got it here.
awesome. Okay, now sure. Yeah, go for it.
It's just a syntax question.
Yeah.
Or you put a -1 inside the, inside the brackets. Yeah. Does that mean you go to the end, or you're going to the end and coming back one?
No, it's a last token. It's a so. Where's the minus one here? So this minus one is the for document management would be the word sad.
I mean, so it's a way of saying grab everything in the string.
No, in the essentially what it does is if you can have a list of 0, comma, actually no, you know what, I'll just use this. For everything I wrote here, the 0, comma, 1, comma, 0, dot, this whatever I call it, a equals 0, comma, 1, comma, 0, a bracket negative 1, we'll call this 0 right here. A bracket negative 2, we'll call this 0 right here.
Oh, it's calling the last one.
Last one, yeah. Because you can't call it negative 0 because that's just
Right.
0.
Right.
That just becomes the first one.
So that's calling the last token, which is the last word.
Yeah, last token, which is the last word, and that's actually a really good question because in this case, we're just using the words as is. I'll tell you what I mean by that. For BERT, right, which is one of Google's language models, we'll talk about it in a later class. But briefly, it splits not a sentence into just tokens. What it'll do is, for the sentence, I am feeling sad, as opposed to I, comma, am, comma, feeling, comma, sad, it'll be I, comma, am, comma, feel, hashtag, ing, comma, sad. It'll be like, as opposed to, 1, 2, 3, 4 tokens, it'll become 5 tokens. There's an extra token for the suffix or whatever. So it lemmatizes it, which cuts it off in order to increase its vocabulary size. That's essentially what it does. But yeah, I hope that answered the question. I think I skipped over a brief bit when I was talking about the whole YouTube live thing, so I'll just kind of scoot back a bit. So named entity recognizer, wait, before that, yeah. This is a tokenizing thing that I'm talking about. So for each token in the document, which is defined at the top, you're splitting it and you're printing it. It's just how it's splitting. So NJ, comma, Princeton, comma, public, comma, library, comma, is, comma, awesome, comma, period, comma, enter, and comma, link, and that's the Princeton Public Library. Now, this is actually pretty important because I wanted to signify the importance of one of the things that this pre-trained spacing language model can do. I'll do that later. Now, key concept is named entity recognizers. So why would we need this thing called named entity recognizers? Now, let's say I was a car parts insurer, right? A car insurer. There's been some damage to the car. I've actually run the car into the wall. And as an insurer, I'd have to take a voice recording. I'd be like, okay, here's a car. I'm like, the headlight's damaged, the hood is dented, and the license plate is like gone or whatever, something that you say. Now you need to split car. Okay, the car's parked on the road, the hood is damaged, and the license plate's gone. You need to split the sentence and identify what the car parts are, where the parts are, as opposed to just the word like as other than the words that I'm normally saying like I am stop words, essentially, those unnecessary words. You need to split, like categorize them. So I need to find what the car parts are, how much money was lost from it, the hood appears to be $50 worth, etc. And you want to classify that. Great use case for named entity recognizer. So the insurer comes like, yeah, the hood happens to be damaged, it looks like the estimation is about $50. I'll pass that through this model. Obviously this one won't do it, this is trained generally. You need to train your own one to be more specific. But then you can extract it into 3 columns. You can be like, the item which is damaged was the car hood. Where was it? I mean, it's parked on the road. Perhaps the location would be the road. And then the cost would be $50. Now, it identifies these different, those car parts, money, location. There are all these things called entities. There are pre-trained entities here, which are geopolitical entities, which is a location. So if I say Great Britain, you'll figure that out. Organization, that's a public library. Obviously, one small area you can see here is NJ should be recognized as a location if it's a public library as an organization. But those are the costs of loading in a small model. You don't get the super high accuracy. But for obviously you're saving on speed, but the accuracy isn't that high. And there are cardinals, which are numbers. There's time. It identifies all sorts of weird things which you can use for whatever use case you want. So that's one fundamental thing, named entity recognizer. Another thing, I already talked about this earlier, dependency parser identifies the type of word, type of speech, sorry, that's what it's called. Type of speech and how it is relevant to the other words. And this is really important. I mean, I haven't used this in any use cases per se, but if you happen to be a big, literature fan, I guess you can figure it out. It's as opposed to doing it manually, you can let the program do it. Yes?
When you
train the name entity recognition, do you convert it to the word embedding first?
Sorry?
When you train a named entity recognition, do you use the word embedding first?
You have to use the word embeddings itself because you can't use a specific words. It's not a dictionary like
No, I'm asking you like when Spacey did it. You know what I mean?
like space.
Like if I was to train my own
Mhm.
NER system, would I
Right.
have to use some sort of word embedding like first before training it?
I don't know. You can use BERT for this use case, but yeah, I think you're saying the right. BERT might be a bit overkill for this stuff because like BERT is like something in the order of like 300 million parameters. But the right idea, like, you do need a language model or word embedding before doing this aspect. You can't just feed in random words. You need to convert it to numbers and then do this. Okay, sorry. Could you repeat that? I'll try to answer it again.
Okay, so I want to create my own named entity recognition. Let's say
Sure.
a bidirectional LSTM, right?
Okay.
So to do it, do I feed in the words or do I feed in the vectors?
Feed in the vectors, but for a bidirectional, okay, whatever. The choice of models is beyond me, but that's okay. The whole point is you have to feed in the vectors as input to the named entity recognition. Any other questions? Okay, so we've covered two key use cases. Now let's look at the different types of words. There's stop words, and the, it, well, I'm not sure about it, but and, the, and, kind of prepositions, stuff that doesn't matter too much in the context. And those are what stop words are. You can get those stop words by NLTK, which you mentioned earlier. NLTK, it has it in a huge, I'm not sure how big it is, but it has it in a list of like, comma, and, comma, am, whatever, all those stop words. And, you can use that, and there's some chance you can either take away the stop words to get only the key words, or you can keep the stop words in there for context. It depends on what you want to do, and it's a choice. You can just experiment different ways of doing it. Lower, it's quite literal. Is it a lowercase? Is it lowercase? Is it upper? Is it uppercase? ASCII is quite literal. Is it an ASCII character? And is digit, is it a number or not? That's kind of self-explanatory. And then what this does is, now let's take a look at the original sentence, right? NJ Princeton Public Library is awesome. Now we take away the stop words, and is it a stop word, therefore it's NJ Princeton Public Library, awesome, enter, blah, blah, blah. As I said earlier, it's a choice. If you are choosing to get rid of that context, it's up to you, and you could get better accuracies and speeds from it. Now these are the stop words that I'm talking about, this list that's over here. And in my personal opinion, I disagree with the fact of removing stop words, because unless you have a huge text and you have to remove those stop words, then yeah, go for it. But if it's a relatively small text, just keep them, because prepositions do matter with respect to the meaning of the word. So in my opinion, I'd say keep them. And there is some research which is supporting that idea too as well. And it's the same, just different explanations. Awesome. Now this is also good because I wanted to talk about exactly what I mean by the word vector. Now you can see this is the dimensions of these, the word vector itself, these are all coordinates on the n-dimensional plane where you feed in a sample word, and then the output you get is a list of coordinates like 200, 300, in this case 384 dimensions. But you feed in those kind of coordinates, and then boom, you get the similarity. And obviously now you think about it, you can't use a regular distance formula like the square root x2 minus x1 squared plus y2 minus y1 squared. That won't work because it's not 2 dimensions. Therefore, you had to go back and use cosine similarity. I think that's Chaparro index and other equations which are available online in order to find the matchingness of two words. Hope that explains. I mentioned all these concepts before. I think it's just more of a visualization of it, and so was this embedding projector. And there are different algorithms to. This is based off of Word2Vec, and as I said earlier, there are different algorithms different data sets with different algorithms that you can use to generate this, and it's just a matter of experimenting. Which one works better for you, and you just use that and move on. However, I would like to mention, not too many people use Word2Vec anymore. This is not history, but I'd say kind of getting there, because although language models are really heavy and clunky in size, like they're by the order of gigabytes, it's a bit more, it's a lot more accurate. And it's just an overall better solution than these word-to-vec models. But we're going to get to that maybe next class.
So what's the,
This is not on YouTube, but it's going to be put on there.
Language models,
Yeah.
such as contextual. I'll give you the precise term. It's like deep contextualized language models, which are inspired from this thing called transformers. So since we're on the topic, I'll explain it briefly. Say I speak English, and let's say somebody else just speaks French, nothing else. We both know this language called language X. So I take English, I convert it into language X, that's my encoding. And I decode it back into French, which is my decoding aspect of the transformer. Essentially, instead of directly translating it and by converting it to this language X, you're able to generate more context, because it's not a one-to-one translation. You can use a dictionary and map, like I am feeling good is like je suis, bien or whatever. But you can't just do that one-to-one mapping. You have to, the context differs across languages. So transformers uses this thing called attention, this attention mechanism, which essentially says, given the context, the same word has different meanings because of the contextual words, and you use that in order to generate this language model. You don't use word-to-vec anymore. So those deep contextualized transformer models are what people use to generate those. And if you would like to read any academic papers, you can search up Google's BERT, as I was talking about, or OpenAI and GPT-2. They're both really great examples of transformers applied to language models. Awesome.
how recent is that?
Transformer was 2017. The concept of a transformer was 2017. BERT was 2018. GPT, the original GPT, Generative Pre-trained Transformer, that's what it stands for, was also 2018. And then the newer one is 2019. So they're very, very relevant within the last 1 to 1.5 years. And they're constantly outdoing themselves. And if anybody's heard of GLUE, which is the, I don't remember, General Language Understanding Evaluation dataset, the GLUE dataset, that has the top of the line for each and every one. It's often not just one language model, it's like a combination ensemble of like ExcelNet plus BiDef, like bidirectional attention flow, and different other models in order to get a better output. But again, as I said, those are pretty concept-heavy topics, which I'll be covering in a couple classes. Great. Now we're done with the theory of today's class. Now we'll just quickly apply it to the Twitter use case. So, I mean, I'm not going to go too deeply into this. Also would like to mention that I have put in my personal credentials here. And
Thank you.
what's up?
Thank you.
Yeah, hey, yeah, you're welcome. It's free credentials, but I'll probably deactivate it right after this class. So feel free to use it while you still can, I guess. Anyway, these are my private tokens. But the summary of what we're going to do is we have our keyword. But the method of getting tweets is not something that I created. It's been there for a long, long time. So I just had to copy it from the internet. So nothing here. This entire class at the top is not original. But at least it gets it into this format called a data frame, which is, as you can see here, data frame. Very, very common tool used in data science. I hope they're going to talk about it in the Python for Data Science class in the next couple of weeks, like tomorrow and the weeks ahead, because it's really useful in machine learning. Anyway, so let's skip that part, but take away the spaces here because that'll throw an error. And essentially, we're getting our text. I'll reload this. I'll run this. Okay, so while this is all running, we want to get our text, convert it into data frame, split it based off the sentiment. I'm going to try to use as like not politically charged words, although they are very polarizing, so it'll be easy to see the differences within it. But through that, we can generate this thing called a word cloud, which essentially is a visual description of similar words together. And everybody's probably heard of a word cloud. It's like the more times the word appears, the bigger the word, and it's pretty easy to visualize, a given sentence in that manner. But sorry for the speech. I'll get there shortly. And this.
Yeah, you got that little issue down there. We'll have to fix it.
Okay. I'll try to open
Not
an
that
existing one because for some reason my credentials aren't working. So although I have created and used my credentials, that is off the books, I guess.
Do they only work for one person?
No, it should work for me. I tried this
Okay.
before. I don't know why it's not working anymore, but
Because it works for me.
It works for you?
Yeah, and actually, I just have to change your next cell.
Change my next cell?
No, go to, yeah, stop. What number is that? Example equal data, and then you're referencing the data frame.
Yeah.
You have strings in there. You have to put, dot str, dot strip.
No, yeah, I did this before. I don't know
Okay.
why. I guess it's. I'm sorry for
Well-
that. The IDs must not be translating. I guess
Because
that is.
if you put info, just look at the info, you'll get the fields.
I'm sorry.
So underneath that statement, type data dot info, or open close paren. No, not well. You could type it anywhere, but you'll see what's inside of that data frame, which it is a data frame.
Okay, that's fine. It's okay. No big deal. I'll maneuver this into a different scenario. That's okay.
It's simple.
Those credentials are different from what,
Yeah, exactly.
Yeah, just,
I think that's the
right.
problem. I'll check the credentials.
So I grabbed the text.
Sorry, guys. Just give me a brief minute. I'll quickly try to get this back up and running.
Second.
1 second. It's 2 minutes, and I will get this back in range.
So you have to
Should work.
right.
Yes. Okay.
Blah blah blah.
Great. It worked finally. I was using a different notebook, and that's because I have commented that out. That's okay. I'll delete that. So that should. Okay, now here we're going to visualize the data frame. Sorry for the brief hiatus. It's just that I was running a different notebook and the credentials were different. Thank you for pointing that out. But we're getting tweets of related to the word college, which is a new word that I tried. I put Princeton before and it was not good. So I took it out. I put a different word, and you can see the columns we have are the tweet ID, what text it has. The author, which is just a Twitter object, and as you can see here, different metadata that we can use. But for the sake of the session, we are not going to use it. And all right, that's interesting. But we're not going to use this and the other metadata because it's unnecessary. We just want to visualize, split the sentiment, and then visualize the tweets. Great. So let's take a look at the sentiment here. So overall, across the first 5 tweets, you can see that the first one is positive, second one's negative, third one's pretty positive, it's 0.7, it's really high. So is the fourth one, and the fifth one is a bit negative. And for anybody who may be a bit confused about why the fifth one is actually the one with the number 4, is because indexes from lists start at 0, not 1. Great. So yeah, let's create this word cloud. Interesting tweets. Very low tweets. Let's take another word. Does anybody have any suggestions that you would like to put in for keyword in this class?
You have wall. I just did wall. I don't know what.
Wall, yeah, wall is a classic. I mean, that at the point of this, when we first created this notebook, I think I'll tell you exactly what happened. Well, not a lot of them have to. All right. I mean, not the worst thing in the world. These are.
Yeah.
Irregardless of sentiment, these are just the words that are mentioned in the tweets. Obviously, the user and the wall, the vets, paying, military, whatever, and these are the keywords that are identified in the tweet. Now let's take a look at a word cloud with a positive sentiment. What that looks like. Okay, this is pretty good. I mean, it's not horrible. We got promise in there, thing, word, whatever. But I'm telling you, these things get pretty weird sometimes. We have no control over the tweets, so
Can you scroll up?
Weird answers.
Up.
Up?
Yep. Stop.
Sure.
Yeah. La 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 la. Oh, where's that one?
What's up?
All right. I have an error. I just didn't know where it was. Can you just go up a little bit?
Sure.
Yep. Keep going. Yep. Keep going. I'm trying to understand what the data object is, or the example object.
The example? Oh yeah, I deleted that because.
Aha. Okay. Well, that's,
yeah.
Okay.
I'll put that back in.
So no, it's fine. So just go right to. So where are you defining? Oh, data, get tweets. So you just were not using example. Okay, no problem.
Yeah, I deleted it before because
Yeah, there was a
it
problem.
was in the
No
form of a
problem.
list, and this is in the form of a data frame, so it doesn't commute. The properties don't commute. That's okay. So this is for the pro one. Now let's look at the negative one, which is pretty interesting. I mean, in general, the negative sentiments appear to be wrong.
Okay, very good.
Okay, let's just not cover this too much because I don't want to get into any political stuff. But fact being that they're positive sentiments and negative sentiments within text, and we can visualize it in word clouds. You can put whatever word you want in there, and you'll get what Twitter thinks. And it's not always a good thing because Microsoft built some sort of bot. I don't remember the name of it. It was just trained off of tweets, and it turned out to be not a good bot. It was bad.
It was called TED.
TED?
Tay.ai.
Oh, Tay?
It became like a Nazi within like a day.
Yeah, it's not fun.
Interestingly enough, though, China has something very similar, like Microsoft Research Asia, called Xiaobing, like Little Ice.
Yeah.
And
Little
it's
Ice, you said?
Little Ice.
Oh, Little Ice.
It's like the same thing, but since China's like a lot more controlled, it's like the most popular thing ever.
Yeah, I mean, it's nice, but the Twitter world is a weird world indeed. And that's great. So now let's think about what we can do with this text. We've looked at tokenizing, looked at sentiment, we've applied the sentiment here. Now one thing you can see is what words are here which make no sense at all. Why are the words RT and RT quite literally being retweets? Why are they in there? They technically don't matter to the tweet fundamentally, so we can take them out. We can remove those specific words. And it's similar to removing stop words. And essentially, sorry, that's it for the text positive one. But essentially, once you take away these unnecessary words, you're just going to be able to get better insights from the tweets that you have. And same thing with the negative, and you just recreate it. And sorry, I did not. This one is applied to the positive text. So let's quickly do a text negative, and let's create that. I'll quickly copy that here, and I'll copy that here. Now let's make that less than 0. And put it up. Okay, I'll check why that wasn't working, but that's fine. Point being, you can do any pre-processing that you need, and you can create insights from these words. I know I've talked about a lot today, and this class was mainly just brushing over these concepts. In theory, I've worked more with the more advanced language models that I was talking about earlier, the BERT and GPT-2. That is the focus of my internship this past summer. And I really do want to talk about that a lot more because although they're really, really complicated, and in a weird manner they use geometry a lot more than I thought they would, which is not my favorite subject, but they use geometry a lot more than I thought they would in order to, physically the coordinate system becomes very, very important. So it's fundamental that you understand why these coordinate systems exist as opposed to just creating those vectors or creating something that doesn't really matter, because through that coordinate system is how we can find the relations between words and also change the context of the word which is generated change the word vector which is generated based on the context. However, a problem with language models is, I'll just get into this briefly, you can't exactly do a similarity check with any word because I can't do blue and sad again. What I have to do is I need to give a context for blue and give a context for sad because the word blue and the word sad would be different on its own as opposed to in its own context. One keyword that I've mentioned a lot is the word context itself, and just to clarify, it is the surrounding words, the words to the left of it, the words to the right of it. It's progressed through first looking at that individual word, looking at just the words from the left, looking at words from the right, and also conjoining them. And that's what BERT does, is bidirectional, in that it just feeds in both directions of the sentence. So, whatever. Any questions on context, word vector, sentiment, why we need to clean data, how we clean data, and what tools we use to clean data? That's kind of the whole gist that I was trying to go on for in this session about whatever I talked. And I do understand that I talked a lot, and sorry for that if I may have caused any heads rolling.
I have a question not about the list above, but
yeah.
Just on how you evaluate a neural language model. I mean, I've used Blue Score and all that. I don't think it's very good.
I mean, Blue Score is for translations, right?
I know.
Yeah, so how you evaluate it, there are different ways. You can unify a layer. Okay, so you know what? Great question. So let's get to the topic. How these language models, essentially you build another model off of it. You put an RNN or an LSTM, which long short-term memory networks or recurrent neural networks, after the input is coming from this embedding. And I'll talk about that next class actually, about those kind of deep neural network models that we use for it. But if you look at BERT and whatever, GPT-2, it just boils down to one specific layer. You get the embeddings, you make a prediction with it, that's it, no complex stuff. I'll talk about how exactly it works, but how to evaluate it, to answer your question, would be you have a unified layer after the embedding itself. So I use love to get some word vectors, I use word2vec to get some word vectors, and I just have the same layers off of it to make the same prediction with the data. And whatever gets a higher accuracy, I would choose.
Like an autoencoder, how well does it actually predict itself?
Exactly, just like an autoencoder fundamentally.
Well, that's better than using Blue, I think.
Yeah, the Blue Score, it's pretty weird because Blue Score goes from 0 to 100, but 70 is the 100. And what I mean by that is any score over 60 to 70 is better than human translations. It's quite literally to the dot. Because I can say the same sentence with the same meaning in like a million different ways with different words. Therefore, Blue Score, I agree with you, it's not a perfect evaluator in my opinion, but it is used for neural machine translation.
Well, I was using it for image captioning generator.
Really?
And so, yeah, I mean, what else are you going to do? And compare it, and it really does it pass the smell test. You read it, is it a sentence? Is it already good? Whatever, but even so. Okay, not just me.
Yeah, sure. Any other questions before I may just dive into something else?
Oh.
What?
Sorry, I'm the only word I know these by. Latent Dirichlet allocation models.
Yeah, yeah.
So they're like latent class vectors of the words, and so it's a way to see which things hang together.
Okay, yeah.
Like to sort of partition or no, I don't know if it's more like grouping columns or grouping rows, but it generates a reduced dimension.
Yeah. Speaking on the topic of reduced dimensions, I want to talk about that. I was going to finish two topics. Hope that'll take up 20 minutes of time. So two topics. One is dimension reduction. Another is the importance of a domain or some sort of contextual focus in these models. First is, what's called dimension reduction. Now there are many different algorithms for dimensionality reduction. One is called PCA, Principal Component Analysis, and T-SNE is another one. But how do we visualize this 200 dimension thing into 2 dimensions or 3 dimensions, like the TensorFlow projector? It's a lot difficult. It's not a lot. It's very difficult in that you can't preserve all the data because you're going to lose some data. It's like a lossy compression. But they're really important because if you can't deliver the models that you created in some sort of visual manner, then you're losing the whole point of them. Because at least when you're trying to sell these or whenever you're trying to present these, you can't just create a model and you can say, here's the model, here's the accuracy. I mean, to some extent you can't do that. But it's also useful to visualize the results of the model in a manner like that 3D analysis. So there are different algorithms, and whenever you have time, if you want to play with it, it's a great way of learning the intricacies of the model and how they're created. Now to another part, which is the domain and why that's important. In these language models, we use general language models. We use pre-trained language models. Now, while I'm not throwing any shade at pre-trained language models, they're great for these kind of classes. I wouldn't say I would use them everywhere. At least, so let's forget about BERT. Let's forget about GPT. Let's forget about all of that. Let's just look at word2vec, those kind of language models, pre-trained, like basic models. In that scenario, why would you use a general language model if you have some? So say you're doing something in the medical domain. You want to train on something in the medical domain in order to get better results. Otherwise, your accuracy is going to plummet. You're going to get like below 50% or below 40%, depending on how many classes you have. And that's the importance of said domain in these language models. You first, although it takes computational resources, in prior experience, it is more of a benefit in order to give in your data, at least in these language models, in order to give in your own personal data to train it, if you have it, because otherwise you're not going to get proper results. You're going to have to make sacrifices. When you get into the world of BERT, GPT-2, and Elmo, some things that are pre-trained, they're simply pre-trained on billions of words, so that context is preserved such that you only need to fine-tune it a bit. You never need to retrain it, because nobody has the computational resources to pay like $100,000 to build. Well, I mean, some people do, but it's not worth it to pay $100K for every new model that you're trying to build. So one important thing to consider is the value of domain while creating these models. And that is the conclusion of my session. It should go up to 8 o'clock, but for now I think I have covered a lot of the topics. I don't want to go into a new one without messing up. Like it's going to take really long if I'm going to contextualize language models. So I'll just give some suggested readings if you like. And one would be to explore Spacey's documentation, because whatever I said is only scratching the surface. This has a lot more things that you can ever imagine, and it's really, really useful, because in a lot of the use cases that I've done, you go to these code examples, and it gives ways to train your own entities, train better language models that you can explore in your own free time. Another one is to go to Siraj Raval's YouTube channel, SIRAJ, space RAVAL, that we are a sub-organization of the main School of AI, and he has a lot of useful video links about these topics. So yeah, next class I will be talking about RNNs, LSTMs, bidirectional LSTMs, GRUs, data recurrent units. Not too technical, but enough that we fundamentally understand before rushing off to the the new hot topic of transformers, because that really did revolutionize NLP. Before we run off of that, I wanted to set our baseline straight, and so we can fundamentally understand why these language models do what they do. Okay, 30 minutes earlier, which is quite surprising, but other than that, I'm done from mine. If anybody has any questions, any comments, would like to talk to me, please feel free to contact me via email, and I will stick around for another 15 minutes with any questions that need to be answered. So thank you for your time, and I hope you have a great day.
Nice job.